Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of electrical circuit. So at this chapter, we would like to talk about final component, inductor. If you guys remember, we talked a lot about resistor. We talked about the capacitor and how it can discharge, what are the capability of that, what was the physical condition and infrastructure of that guy. So right now, we would like to shift our focus into the final component, which is inductor. Without further ado, let's talk about it. So as I just told you, we do have three important components in our some kind of electrical circuit concept. The very first one was resistor. We talked about it. The next one was capacitor. And right now we would like to talk about the inductor and capacitor. Both of them are considered as a place that you can charge the energy, but in different forms. If you remember when we were talking about the capacitor, we had two plates, the first plate and the second plate, and those plates were in parallel. In the meantime, we had another core between. Why we had that core? Because based on the formula, C is equals K epsilon A divided by D, by putting a core rather than air, by the way, we can increase the capacity of our capacitor. It means that we can charge or we can store more charge inside the capacitor itself. So right now we would like to talk about the inductor. Inductor is going to do the same thing as capacitor, but in different format. This guy is going to store the energy into the magnetic part. We will talk about it in detail, but this is something that you have to know. So it means that a passive electrical component that stores energy in a magnetic field when current flows through that. We would like to talk about the currents. We will talk about how actually everything would happen. We will talk about the flux and a little bit of formulas itself. So for the symbols, what do you have the L, which is considered as the capacity of the inductor. We call it as inductance. Then we do have the unit. If you remember, for capacitor, we had Faraday. For your unit of inductor, we do have the Henry. Why we do have that? Obviously because of named after the person that found some kind of invent or at least discovered this fact, Joseph Henry. And the very important thing is that this guy is going to oppose the change in current. If you guys remember about the capacitor, it was vice versa. It means that your capacitor didn't like the change in voltage. In the meantime, your inductor doesn't like the change, but in current. So most of the time we use the microhenry and we use the millihenries, and Henry is a very big number. So mostly it would be used in the power applications and etc. So let's talk about it in detail. Let's talk about the physics. Let's talk about the very first rule, or Faraday's law. What does it say? The Faraday's law explains that how changing the magnetic field induces the voltage, we call it as EMF, that opposes the change in current itself. So what does that mean? Imagine that you have the solenoid, and based on the rule that we call it as a right-hand rule, if you consider the thumb direction as the direction of current, you can say that the four fingers that are getting close is the direction of flux. So flux actually the thing that we would like to talk about it a lot. We just call it as the flux itself, and if you guys remember, the units for that was phi. So at this point, imagine that I do have the solenoid, and the solenoid is like this. Then I do have this guy is connected to my source. Obviously, this guy should be connected to somewhere. And based on that, I do have the current inside of this guy. By making the current, or by considering the current, if I say that current goes this way, I can say the amount of voltage or the voltage that it gets induced inside my inductor would be in this way. It means that this guy is considered as back-EMF, or the amount of voltage that is going to fight against the changes. The formula is simple. The VL is equals L, which means the amount of capacity of your inductor or inductance, times di over dt. But one thing that is hidden in this formula is negative sign. It means that when you have the changes of your current in the positive side, you do have the voltage on the negative side. So it is very important to consider that current flows, it means that it's going to create magnetic field. This magnetic field is based on these guys, which we call them as flux or phi. And then we are have the coil as a concentration field. So we can have in the wire, but what's the usage of that? We need to concentrate some kind of the flux itself in order to have some voltage, right? So this guy is called as a flux linkage. Then you have the changing in the current, di over dt. And by the way, di over dt is just a small symbol for delta I over delta t. It means that your current should change over time if you want to consider something that actually is going to induce. So it means that the changing the magnetic field, and changing the field is going to induce voltage. We call it as back EMF itself. So as we had the formula related to capacitor, obviously we have a formula for that. The L amount of inductance, which we know it as Henry, let me just call it, we know it as Henry, is going to n to the power 2. N means that the number of turns that you have for your coil to the power 2 times mu, which we know it as permeability. What is permeability? Permeability means that how willing your some kind of area, which we are talking about, by the way, as you guys remember, we would like to have this solenoid in order to concentrate all of the fluxes that this guy is produced inside itself. By concentrating that, we can make sure actually we do have the inductor, or we do have the energy that is gets stored inside the magnetic field. Obviously, sometimes we use the air, so it has a permeability. It means that it has the willingness to accept all of those concentration or some kind of the linkage. But the air has a very small amount of some kind of permeability, which we call it as mu 0. It's 4 pi times 10 to the power negative 7. It's some kind of nice to know that. So their unit is Henry per meter. In order to increase that permeability, we are going to use the core, iron core, metal core, whatever you can use. And that specific thing is going to have something, as we call it, as the permeability ratio. The permeability ratio says that how stronger that specific material is against the air itself. For instance, at this point, I do have a material that is going to be 500 stronger than the air itself. So finally, my permeability is going to be what? Is going to be 6.2 times 10 to the power negative 4. Why we are doing that? Because we would like to use that guy in order to increase our mu. By increasing the mu, this guy would increase, and obviously on another hand, you have L is going to increase as well. Then we do have two other some kind of concept. The A is bound up area, that is flux is going through that, which would be over here. Obviously, the area would be considered as a circle divided by L. L is the length of your solenoid itself. And finally, for instance, if you do have some kind of couple of numbers for yourself, you can just put it over here. And finally, we do have L. Again, as I just told you, microhenry and millihenry are very common, but Henry is a very big number. So mostly we don't use it in electronic part, or at this electrical circuit section. Another important thing that we have to know is about the behavior of your inductor itself. As I just told you, inductor, capacitor doesn't like the change. In capacitor, the change was about the voltage, but at this point, the change is about the current itself. So as you guys remember, we had a formula V equals to negative L di dt, but we don't consider some kind of the negative side itself. I'm going to say that L di over dt. Again, d means that the small changes of that variable, which at this point is I and t. So V is equals L di dt, and this guy cannot change that fast. It means that at the beginning of the point, when you connect your inductor to the circuit itself, you do have the huge amount of current that would like to pass, but your inductor doesn't like it. It means that at this point, your inductor is going to act as what? As going to act as an open circuit or open switch. Nothing would pass through. So the current would be 0, and we do have the maximum voltage drop, because if you consider this guy like this, we do have a resistor and we do have the solenoid between. At the beginning of the point, no current can pass through your inductor. It means that this guy is gone, and all of the voltage that you have for your inductor is going to be as the same as all of the voltage that you have for your source itself. So it has the maximum amount of voltage. But what would happen after a couple of time? Obviously, if you guys remember, for the capacitor, we had 5 tau, which means that after 5 tau, your capacitor is getting fully charged. When your capacitor is getting fully charged, no current can go through that. So everything is vice versa when you compare it to inductor. At the same time, when your inductor is getting fully charged, it means that as t is equals to infinite, or somehow we call it 5 tau or 6 tau, your capacitor is getting fully charged and no changes in current we do have, so voltage drop is going to be 0. So it is important. At DC steady state, the inductor effectively disappears. It just becomes a short circuit. That's a good thing about that, obviously. It means that it's getting fully charged. Another important thing that we have to know is how we can measure the amount of energy that is getting stored inside our inductor. If you guys remember, we showed with you in the capacitor itself, it means that half of CV to the power 2, which was with Joule, we do have the same concept in the inductor. But remember that we do have the magnetic energy storage. Is equals half of L, which is the inductance, I to the power 2. So inductors store the energy based on this current itself, unlike the capacitor, which is stored based on the voltage. So energy is stored, for instance, if I do have the L as 100 millihenry, and if I do have the current as 5 ampere, I can just simplify the amount of energy stored inside of that. Sometimes the question is vice versa. It means that they will tell you that how much the current should be in order to make sure that I do have 2 joules inside my inductor, which is stored in the magnetic energy. So obviously by just rearranging some kind of formula itself, you can find a specific current. So it is very important to know that. As I just talked about it, and the timing that it takes for an inductor to get charged is 5 tau, just like the capacitor. But the tau, or the time constant, follows another formula. The tau is equals L divided by R. So L obviously just an inductance of your inductor, but R is the amount of resistance that your inductor can see while there is no sources. So it is very important. Most of the time when you only have just one RL, it is not that hard. But when you have the combination of resistance and also your inductor, and in most challenging condition you have the capacitor, which we call it as RLC circuit, it would be so important. So at this point we just assume that tau is equals L over R. Again, what was the definition of tau? Tau means that how much time does it take for your inductor to get charged 63.2% of its maximum. The maximum would happen at a time that your current would be maximum. It means that your inductor is just a wire, just a short circuit, and when you have that, or when you have this timing, you can use it. Why? Because you can see after 5 tau, your inductor is getting fully charged, almost fully charged, which is 99.3%, which is a very good one. We also do have another formula for that. The formula related to IT, because as I just mentioned, your current is going to change over time, or the amount of current over time is equals to V divided by R times 1 subtracted by e to the power negative t over the tau itself. Obviously, one missing thing that we do have over here is the timing. And based on the question itself, for example, would say that after 5 seconds, how much some kind of current you see, you can finally find this value. And as you guys can see over here, after 5 tau, or maybe more than that, this value would be something around 0. So your current would be V divided by R. In an RL circuit, the L is gone. It just acts as a short circuit. So you have R and you do have the voltage source. Another important rule, or another important the formula is the voltage of your inductor is V times e to the power negative t over tau. The V is the voltage that your inductor is connected to, or we can something as saturated voltage, and t over tau, again, just like the previous variables. And again, as you can see, after time 5 tau or 6 tau, this guy is almost getting 0, and it means that the voltage of your inductor is getting 0. So imagine that we do have a condition that L is 50 millihenry and the R is connecting in series to that is 10. So we can find the tau. It means that 5 milliseconds is the amount of time it takes for my inductor to get charged 63.2% of its maximum. So as I just again mentioned, that at 0 tau, or as soon as you're connecting your inductor to the system itself, the current is 0. It means that your inductor doesn't like the change, so it's going to have the 100% of opposition. After 1 tau, you do have the amount of 63.2% of energy or current, so obviously the opposition would decrease fundamentally. And after 3 tau, you do have 95%, you have this amount of opposition. And after 5 tau, almost your inductor is gone. So it means that you don't have anything as opposition itself. Again, for some kind of example, imagine that you have L as 200 millihenry, R is 40 in series with that, and the voltage that you're connecting R and L is going to be 24. So you can find the tau, L over R, you can find the I max. It means that I max is going to happen at the time your L is completely gone. So what do you have? You have V and R. So V divided by R, and finally current at 10 millisecond is just related to the formula. Again, you remember that I is equals V divided by R, by the way, IT, times 1 e to the power negative t over tau itself. Just put the timing that you need, and after that you can find the current itself. Simple as that. So we do have another some kind of example in order to you guys make sure that completely understand it. Again, try to look at the question itself, try to pause the video, think about it, then you can come again and see what's going on. So at a point that when I do have the RL circuit, my voltage is going to be, maybe I can use another one. My voltage is 12 volts, the R is 6 ohm, and the L is 30 millihenry. So I would like to see what would happen. The very first thing that you have to find, obviously, the tau, amount of time constant. L divided by R, so it's 5 millisecond. Then I would like to find a maximum current. Again, maximum current would happen at a time when your inductor is completely gone. By gone means that that guy is fully charged or just a short circuit. So I max is V divided by R is 12 divided by 6 or 2 amp. Then we would like to see the boundary conditions. It means that at the first point, the T is equal to 0, there is no current. So the voltage of your inductor is 12 volt. That is completely makes sense. No current, resistor is gone. All of the voltages would be on the both legs of your inductor. At T is equal to infinite, or we can call this 5 tau, the VL is 0, so it means that short circuit is happening. And transient calculation is that finding current at 2.5 millisecond. We write down the formula, the V, or the amount of saturation voltage, as you guys can see based on the formula itself, the V divided by R. So it would be 12 divided by some kind of 6 itself, which means that at the full saturation, we do have 2 amp times 1 subtracted by e to the power negative t over tau. Do that one and you have this number as your final answer. So we talked about the charging, but what about discharging? As you guys remember, when we had the capacitor, we also can use that guy as the secondary source. It means that we would like to charge the capacitor, then we would like to discharge it. We had a couple of formulas about that, I don't have to mention, but right now we do have the same scenario about the inductor. But one thing that you have to be careful, that capacitor is going to act as a voltage source, while the inductor is going to act as the current source. It means that when you consider the inductor itself, while there's no source, that guy is going to give you current. Obviously, this current would diminish after some time because, again, it's going to lose the charge. And another important thing that also I mentioned in the capacitor is that the direction of the current is going to be what is going to be opposite of the main condition. It means that if you consider that your current is getting stored or getting charged clockwise, your discharging would be counterclockwise. So let's see what would happen over here. Again, the physics behind this one is that when the source is removed, the magnetic field collapses. So the stored energy that we had is going to force this current to keep flowing. So the polarity, as I just mentioned, is going to flip. Notice the voltage polarity reverse. The inductor is now pushing current, not fighting it. So the equation is what? Is equals to I0, amount of fully charged or the saturated current, times e to the power negative t over tau. And V is going to obviously be going to be in the negative because the voltage is going to be on the negative side. And we do have this formula, negative I0 times R e to the power negative t over tau. So again, the discharge, we do have the tau itself, right? So at 0 tau, we do have the full amount of current as we just talked about it. So nothing to worry. But after 1 tau, this time, it means that how much does it take for my inductor to reach to what? To some kind of discharge the around 63.2% of its amount of full energy, right? So it means that how much does it remain? 36.8%. After 5 tau, this one would be empty. So imagine the scenario that I do have L is equals 100 millihenry. My I0 is 4 amp. It means that assume that I do have the voltage source that at the saturation voltage, it charged this inductor as 4 amp. And the R is 220 ohm. So the very first thing we have to find is tau. Tau is the same. L divided by R is 5 millisecond. The current at 10 milliseconds or 2 tau would be what? Based on the formula that we have. It would be I0 e to the power negative t over tau. So if you calculate that one, it would be what? 0.54 amp. It means that after 2 tau, you're going to have this amount of current. So time drop to 1 amp is again simple. So instead of just having that formula, we are going to use another formula, which means that by rearranging it, you are going to have your t, which at the beginning was your variable, and you put some time, but at this point you have to find it. T is equals to negative tau times ln times I divided by I0. So I is the current that you already would like to reach, which is 1 amp. I0 is the saturation current, the tau is the time constant, and T is the timing. So by putting that, we can find that at 6.93 millisecond, you can find the specific current that you like. So as you can see over here, we do have the very small comparison between the charging and discharging. So for the charging itself, I do have the inductor, it switches off, and then I do have the voltage source. As soon as I close this voltage source, what would happen? At the beginning of the point, I don't have any current. Again, why? Because inductor doesn't like the change. So then at the end, I do have V over R. It means that your inductor is going to act as a short circuit. The voltage is going to be positive, obviously, and the formula related to voltage is going to be two things that I just mentioned. On another hand, we do have the discharging. So at the discharging point, the direction of the current would be changed, right? It's not going to be this one anymore. It's going to actually be what? It's going to be this part. So it means that this current, or at some point we can say the voltage, is going to flip. So it means that at the start we do have the maximum amount of current, and end, obviously everything discharged will be nothing, and the negative would be the flip of the voltage itself. We do have a very small calculation over here. Obviously you can pause the video and you can find those solutions. It's not that hard. And then let's try to compare your answer with these itself. So what would happen if you do have the parallel RR circuit? Because so far we talked about the serial RR circuit. As I just mentioned, nothing would change that much. But the important thing that you have to be careful is what is about your time constant, because it's not going to be simple L over R anymore. Your R is going to be R equivalent, or amount of resistance that actually your inductor would see while there is no source of there. So again, everything is also the same. It means that DC steady state, the T is going to go to infinite. The inductor acts like a simple resistor equals to its winding rod. There's some kind of RL itself. Imagine that we do have a condition that the voltage source is 24 volt. It is connected to the parallel condition of one resistor, which is 12 ohm, and the inductor and resistor 4 ohm and another inductor. So at this point, for example, we would like to do a couple of calculations. V is 24 volt, branch 1 is 12 ohm, and branch 2 is 4 ohm. Why we consider that? Because at its steady state, your inductor is gone. So you simply can find the current, or amount of current that actually your L is going to have after fully charged. So another kind of diagram of that specific question would be like this. It's another kind of question, sorry. It's the next question. Imagine that I do have my voltage source. I do have R1, I do have R2, I do have RL, and I do have the inductor itself. After T is equals to infinite, I do have the voltage, I do have R1, I do have R2, and I do have RL. My inductor is gone. So I can find a combination of these guys. It means that these two and this one, obviously these two are in parallel, is going to be in series with this guy. I can find the total current. At this point, imagine that V, let me just use another color, V is 63 volts, R1 is 6 ohm, and R2 and R3, while they're in parallel, is 18 and 6. So simply, we can do this parallel, add it with that one, and we can find the total current. But some kind of the current rule that we know, we can find the amount of current inside each branch, and we do have 2.57 at specific branch that we have. So let's see another some kind of solution as the final solution related to inductor. Imagine that I do have a condition that my voltage source is 60, I1 is 10, R2 is 30 ohm, I do have 150 millihenry, and I do have RL of 15. So part A is a steady state. I would like to see what would happen after the time is infinite. Obviously, we don't have infinite, we consider as 5 tau. So the R equal would be the combination of 30 and 50, because at this point, we know that our L is just act as a short circuit. So the final, we do have 10 ohm. Then we do have the total R. The 10 ohm plus 10 ohm is going to give us as 20 ohm. So the source current would be 3 amp. By using some kind of the formula that we know related to finding each branch, I1 and I2, I can find the amount of current that goes inside the I2 itself. So this one, inductor current would be 2 amp, and I can find the amount of stored energy. As you guys remember, the W would be half of Li squared. So what would happen if you would like to talk about the discharging? What would happen? At this point, this guy is gone, or this guy is going to act as a short circuit. So right now, my inductor is going to inject the current. How much current? We're talking about the 2 amp. So we're talking about the 2 amp. At this point, we do have another combination. At this combination, my R2 and R1 are going to be in parallel. Then I do have RL is going to be in series with them. So by calculating that, we can find it. And another important thing is finding the tau, because tau would be different. Tau is going to be RL divided by R, or R equivalent. By finding the R equivalent, or amount of resistor that you will see from the perspective of inductor, you can find your tau, and you can find anything that you need. So as you guys just saw, we talked about inductor, another fantastic and very important component in our day-to-day life, fixing electric side. So in the next chapter, we would like to talk about the combination of all of them, R, L, and C. Let's see what would happen if you do have all of them. Again, if you have any question, I would be more than happy. If you have any kind of comment for me, I will explain to you. And if I couldn't, probably I would make another video. My name is Mahmoud Kiasari. Thanks for watching. Have a super great day, night, whatever. See you around.